Welcome back. In the last example, it would have been more convenient to integrate with respect to y as opposed to what we did, which is integrate with respect to x. In other words, we could have taken this interval from y equals 0 to y equals 2 and chopped it up into a bunch of subintervals, and on each subinterval use a horizontal rectangle instead of a vertical rectangle, so a horizontal rectangle, to approximate the area between those curves on that particular subinterval of y. Now, the reason that that's helpful in this particular case is that if you look at any horizontal rectangle from the left curve to the right curve, it's always going to be from the curve y equals square root of x to the curve y equals x minus 2. In other words, the left curve is always y equals the square root of x, and the right curve is always y equals x minus 2. So when we're doing our calculations for the rectangles, it's always the same as we go across our entire region. We don't really have to split up our region into two parts anymore because maybe the bottom function changes. When we're doing an integral with respect to y, we don't have to break it up because the right curve never changes, the left curve never changes, and so we'll be able to set up a single integral. So the area formula is going to become the area between the curves is equal to the integral from here c to d. C would be like 0 in our example 2, and then d would be 2 in our example number 2, of f of y minus g of y dy. So here we'd have to write the curves as functions of y. So write x as a function of y for our curves. And we're going to take the right curve to make sure that everything's positive. We'll take the right curve, or the right x value, and then minus the left x value. Again, it's the same exact reasoning that we used when we chopped up in the x direction as we have when we chop up in the y direction. The visual argument is still the same. So only a slight change to the formula. So in example 3, let's do the same problem as example 2, but now use horizontal rectangles. So we already know where the intersection points are. And I'll just point out, no pun intended, where the intersection points are. Here, the most important values that we want to look at for the intersection points are the 2, the y equals 2, because that's going to be the end of our interval, and also y equals 0, which is going to be the start of our interval. Let's draw along the x-axis, that boundary, and just for fun I'm going to write y equals 0 right here. Okay, so there's our region. Same region, so this is looking at figure 5, but this is the same region as in figure 4, as in example 2. All right, but now what we're going to do is use horizontal rectangles. So I'll draw a sample horizontal rectangle on some little subinterval in the y direction. So we've, quote, raised up this horizontal rectangle from the left curve to the right curve. Now it's going to help to know what each of these curves are as functions of y. So rewriting them as x equals some function of y, and over here x equals some function of y. Now what would it be for the top curve? How can you rewrite, so the top curve is y equals the square root of x, how can you rewrite that as x equals something? So if you said x equals y squared, that would be correct. X equals y squared. All you do is just take that equation, y equals the square root of x, and square both sides. Then you'll get y squared on the left, you'll get x on the right, and you'll get x equals y squared. Notice that that's actually a parabola that's opening to the right. But here we're only taking part of that parabola, this top half of the parabola. Okay, now for the line, what's going to be? X equals what? So if you said x equals y plus 2, that would be correct. All you have to do is take the y equals x minus 2 equation and solve it for x. So add the 2 over, and you've got x equals y plus 2. Okay, so now we're looking for this region here. And I'll just use green to represent that whole region. There. So the total area can be set up in a single integral. It'll be the integral from 0 to 2. So we're integrating in the y direction now, with respect to y, of the right function, the one with the bigger x values, which is y plus 2, minus the left function, which is y squared. That one has the smaller x values. And then we've got a dy at the end, not a dx, but a dy, because we're integrating with respect to y. We're integrating in the y direction. So whenever you see this dy in these kind of problems, you know you're talking about horizontal rectangles, and that everything inside here has to be a function of y. All right, so then we can go ahead and finish this off. Actually one thing before we get there, I want to again emphasize this is the right x value minus the left x value. Why right minus left? Because that's the only way you can get positive sides for these rectangles. If you do the left x value minus the right x value, that's going to be a small x value, let's say like 1 in this picture, minus a bigger x value, let's say 3. And 1 minus 3 would be negative 2. That's not going to give you a positive area for this rectangle, and therefore not a positive area for your region. So we want to do the right x value, which is the bigger x value, minus the left x value, which is the smaller x value, say like 3 minus 1, and that'll give you a positive 2. So it's always right minus left whenever you're talking about finding positive area, which is our goal for this section. All right, so let's finish this integral off. Here I'm just going to jump in and do it. So we got y squared over 2 plus 2y minus y cubed over 3 from 0 to 2. Plug in the 2. Now I wanted to do this because I wanted to point something out. When you have 0, when you're plugging in 0 into here, into the y values, remember that you can just check each term to see if it becomes 0. If it doesn't, it's possible that when you plug in 0, you won't get 0. Like cosine of 0 is 1. That's not going to give you 0 if you ever had a cosine in here. But here, let's just check. Here, if we plug in 0 into y squared over 2, that'll give us 0. And then the second term will be 0, and the third term will be 0. So we can just put a big minus 0, or just not even put anything there. So then when you work out all the fractions, you'll end up with 10 over 3. I'll just put these in parentheses for some emphasis here. When we plugged in the 2, it was all that, and then we had the minus, and then we have 0. So we get 10 thirds. So notice it was the same as example 2. There's actually one more thing I wanted to cover before we leave this section, and that is this. What would happen if the functions changed positions right in the middle of your interval? So just to illustrate this, here's the picture we were looking at before. It's like figure 2. We've got this f of x on top, this g of x on the bottom, and our interval is from a to b, and we've got 10 rectangles here. What would happen though if we took a and we dragged it over to the right, or to the left? Now, when we look at it, we have the interval a to the left of this intersection point between g and f and g. And in fact, as we go from x equals a to x equals that intersection point, g of x is on top and f of x is on the bottom. But then from the intersection point over to x equals b, f of x is on top and g of x is on the bottom. So the functions are switching places as you cross that intersection point. So what would we do in that case to find the area between these curves? Well, if you're thinking that what we're going to have to do is break this up into two integrals, then you're correct. That's what we're going to have to do. We're going to have to evaluate the integral from x equals a to x equals wherever this intersection point is of g of x minus f of x dx, and then set up a separate integral to find the area from the x value of the intersection point to x equals b, where we'll have the integral of f of x minus g of x dx. So we'll just break it up into two separate integrals, figure out the positive area between the curves in the first region, and then the positive area between the curves in the second region. And keeping everything to make sure that everything's positive, we'll always do the top function minus the bottom function. If the functions ever switch places, we've got to break up into separate integrals. Congratulations on making it to the end of 6.1. I hope you learned something new and reviewed skills you've already learned. To celebrate, here's a quick joke. Why can you never trust a math teacher holding graph paper? Because they must be plotting something. Right now, the only thing I'm plotting is to eat some lunch. So take care and see you in the next packet.